So this course is called Low Power VLSI Design. Okay, and it's a very important course with respect to how analyzing power dissipations, especially in VLSI design. Now, one tricky thing that comes is the power dissipation. Okay, so we are making things so complex. We are trying to integrate many transistors, and we are trying to add up features one by one. But then we have not given much importance with respect to power dissipation, right? Now, power dissipation becomes a very important aspect when these days things are becoming all mobile, right? So when I say mobile, it means it can be a laptop which can give you a battery backup of say about 4 days, 5 days, okay, or probably it can be a cell phone, at least giving you a decent backup of more than 1.5 days, right? Or probably it could be your smartwatch, for example, where you don't have to charge it for a week, right? So low power plays a very important role when we design circuits, right? So for many years, power was not given such importance, but then these days things are becoming all digital, smart. So the utilization of power, how much of power is utilized, the power factor, all becomes a very important criteria to think on. Okay, so this is a very interesting subject, right? Low power VLSI design, and we'll be looking into 5 modules. Okay, and before that, just let us look into the course code. It's going to be 20 EC 752A. Okay, and this is going to be for 3 hours the examination. So lectures per week will be having about 3, and there's no any tutorial or practical sessions for this, right? Uh, uh, the number of credits for this course is going to be 3, and as you all are aware, CIE marks is going to be 50, and SE is going to be 100, scaled down to 50, so totaling up to 100. So once this subject is done, okay, so what is the outcome? What are you going to learn from this subject? You'll be able to examine the sources of power dissipation. You'll be able to identify from where is power dissipation happening, what aspect should I actually think on in order to reduce this power dissipation. If in case I tackle this point, will it really impact the power, or is it just going to be nominal, right? So we are going to tackle this point, okay, the sources of power dissipation. Then we're going to investigate the impact of device and technology scaling on low power electronics. Now, scaling is a very important topic, okay, where things are shrinking, things are becoming smaller. Okay, you can remember the calculators that you had previously, the big ones which used to have just addition, subtraction, multiplication, and division. But these days you have calculators which can do much more complex things, isn't it? You can do integrations, you can do differentiations, you can do matrix computations, and not only that, it gives you in the form of natural display, right? You can have it in the form of 33 by 5 example, right? So just because the complexity increased doesn't mean that this calculator has to be still bigger, but then it has become thinner and more smart, right? So scaling is one such factor which has helped us in getting things more compact. Okay, so more work and less space. So that is what we are aiming for. So you should be recalling Moore's law, right? Who says that every 1.5 to 2 years, the number of transistor count is going to increase. It's going to double, right? To be precise. So that trend has been on, and there are processors being fabricated with 5 nanometer technology. So when I say 5 nanometer, the distance between the source and drain is just 5 nanometer. That's your channel length, right? So source and drain is coming so close, right? And right now there's going to be processors manufactured with 3 nanometer technology, right? So scaling empowers all these factors. So next we're going to inspect different low power circuit techniques for digital circuits. So as I was mentioning, most of the devices that we have now are all going digital, right? Moving away from analog, just for the reason that the power consumption is too low, and it's easy to handle because you just have zeros and ones, so it's easy to handle. Next, we're going to distinguish between various architectures and how we can minimize power in RAM. Okay, so RAM is a very important thing because your laptops do have it, your smartwatches do have it, your cell phones do have it, right? So RAM is important because it's like this paging concept, the bookmarking concept, right? So it remembers where what as soon as you open up the browser and then you type Google. Um, at some point, the cache memory and the RAM, it all knows, from where to go, what to pull up, all this stuff, right? So the more the RAM, the faster becomes your system. Okay, so we're going to analyze various energy recovery techniques in low power VLSI design. So energy recovery, right? So this is one interesting thing where you try to get back the energy which has been dissipated. I remember of an article which I was going through where in one of the countries the ACs that are being used, okay, usually there is a hot air that vents out, right? And the room where it is fixed or the hall where it is fixed is going to be cool, but then the vent out air is too hot. So they were able to take out this hot air and convert it back to energy and partly serve as energy back to the AC, right? So in this way, the power consumption reduced drastically. So these are some things, okay, some ways in which energy can be recovered while it's dissipated. Okay. Next, survey research articles on low power design methods in VLSI design. So the best way to go through is reading the latest paper publications, reading the latest journals on what is trending on low power. Okay, so these days low power is very important, as I mentioned previously, because most of the things are all battery operated, right? So power plays a very important role. The less power, the better, because I don't have to keep running after my charger. I don't have to keep looking for an AC outlet, isn't it? So power is an important factor. Okay, so we will be having 5 modules as usual, right? So this is going to be the syllabus. First of all, we're going to use these 3 textbooks. Okay, these are internationally recognized textbooks and very good textbooks, and probably if you can get them, it will be good. You can use it for lifetime. So one of the best is this low power design methodologies by Jan Rebe. Okay, and low power CMOS VLSI design circuit by Kaushik Roy, and the practical approaches for low power, and this is by Gary Ip, right? So these 3 are one of the best textbooks. Okay, anywhere you go to any university, these 3 are referred the most. And I think you must be very much aware with Neil Veste for CMOS VLSI design. So we'll be using the 4th edition of that textbook. Okay, I would prefer you using the 2nd edition because it's much more elaborate. And then in 3rd edition, most of the things are cut out. But then in 4th edition, a different perspective is given. So I suggest you can either refer 2nd or 4th edition. First, you can have them both side by side, and you can use it as reference. So our first module is going to be introduction to low power CMOS VLSI design, and here we'll be looking into why do we need to get into low power, what is the need for low power, and what are the sources of power dissipation, what kind of freedom do we have as a designer, what freedom, what level of freedom with regards to circuit design. Okay, and then what are some trending things in reducing low power, what are the approaches to reduce low power. And then in 2nd module we'll be discussing on device and technology impact on low power electronics. So when I say technology, remember I was talking to you about the 3 nanometer, 5 nanometer technology, right? So that is nothing but the distance that has been maintained between the source and drain. So if I say 5 nanometer, right, so that becomes a particular technology. If I say 180 nanometer, that becomes a particular technology. So for each technology, there's a separate VDD, is a separate threshold voltage. So accordingly, scaling happens. If say, for example, if your transistor needed about 12 volts to operate, here it might just need about 0.8, 0.6 volts. That's it. So that's going to be considered as high value. And the lowest value, of course, it's going to be 0. So introduction, dynamic dissipation in CMOS, and what are the effects of speed, and what are the constraints when I reduce this power consumption? Can I really reduce VDD? If I reduce the power supply, will it operate properly, right? So all those are challenges. I just cannot drastically reduce. Then transistor sizing, right? So I was talking to you about the scaling. So how much size is optimal, and we'll be talking about the SiO2, the gate oxide thickness. So this is nothing but called TOX, thickness of the oxide, right? So if you can recall with the CMOS VLSI designs course, right? So there it talks about the gate oxide thickness. Then we'll be learning on the impact of scaling, right? So scaling has its own pros and cons, right? It's not that everything is a pro and everything is a con. It's a mix and match of both, right? So you cannot say that altogether scaling is best, and it always gives me advantages. No, it's not. It's not like that, right? So scaling also does have some sort of disadvantages too, right? So we'll be learning about this impact on scaling. Okay, then we learn about technology and what are the innovations with respect to low power. See, always you should keep in mind whenever we design new things, okay, we cannot expect 100% result from it, but it's going to be an incremental update from the previous version, right? So in module 3, we'll be discussing the techniques for low power circuit designs. So where we'll be looking into flip-flops and latches, logic high and logic low values, then capacitance. Now, whenever there is a junction, right, there occurs a resistance and a capacitance. As you all know, this is called as parasitic resistance and capacitance. So most of the time, this output is actually pulled down. Okay, the performance reduces because of this parasitics. So in general, we can call it as parasitics, the resistance and the capacitance. Now, these parasitics are not designed by the designer, but then it happens on its own, right? So we do not have much control on it, on the parasitics, okay? But then we can to an extent, provided we have some measures. Low power static RAM architectures. So here exclusively we'll be dealing with memory circuits, right? There are a lot of roles, once you graduate out of your engineering with respect to memory designs. Okay, you'll be recruited as an analog engineer, as a memory designer. Okay, so these fields are trending right now. So the organization of static RAM, how static RAM operates, how you have this read-write cycles, then MOS static RAM, memory cell, how are the banks working, the register banks, reducing voltage swings on bit lines. Okay, so these bit lines are nothing but your read and write lines. Okay, reducing power in write driver circuits. Okay, so when you're writing information, when you're extracting information, okay, read and write. Reducing power in sense amplifier circuits. Okay, method for achieving low core voltages from a single supply. So using single supply, how we can reduce the voltage that is needed. So next we'll be looking into low energy computing using energy recovery techniques. Okay, and here we'll be looking into energy dissipation in transistor channel using RC model. R and C are the major sources of contribution, the resistors and capacitors. Then we have energy recovery circuit design. Okay, I gave you an example on the AC, right? So what kind of circuits can we have in order to recover whatever power that we have lost? Designs with partially reversible logic. Okay, so if we can, instead of 1, can I use a 0, thereby reducing the power? Next, supply clock generation. Okay, so how can I design my clock so that things become more smooth? So this was about your syllabus that we are going to discuss for this course altogether, right? And as usual, we will start off with the first module, which is Introduction to Low Power VLSI Design. Okay, so as you all are aware, the course code is 20EC752A. Okay, and the course name is Low Power VLSI Design. And we're going to start off with module 1, which is going to be the introduction to low power. Basically, this is going to be the motivation for low power design. Okay, so this one we have seen through, right? So the first thing is the motivation. Why do we need to go with low power? Okay, so system performance has been synonymous with circuit speed or processing power. So whenever I say performance, okay, so it means that I am comparing it with speed or processing power. Let's take the example of a processor, right? So processors usually calculate or they operate in the speeds of gigahertz, right? So as the number increases, let's say it's 3.5 gigahertz, when I compare to another processor with 4 gigahertz, then I can say that this 4 gigahertz processor is able to calculate many things per second, right? So these are going to be millions and millions of instructions per second. So hence we are able to have faster systems. So whenever I say system performance, it means that we are talking about its speed and we are talking about its power, how fast it's able to process power. So you can take the example of probably if you have shot an 8K video, right? And maybe you're trying to process that video. It takes a lot of processor power, you know. Maybe if you worked on 4K video, right, you would understand how much time it takes for the rendering to change from one format. Maybe if you're doing a video editing, right? So all this depends on your processor. So I can say that the performance of the system is high if and only if it's fast and it can perform things in a proper way. So let's take the example of a microprocessor, right? So this can execute instructions in MIPS, which is millions of instructions per second, or millions of floating point operations per second, right? Now you can remember the processor 8086, right? So this cannot handle your floating point numbers. So there should be a separate processor which deals with floating point. So that is nothing but your 8087, which is your arithmetic coprocessor. So this arithmetic coprocessor helps in calculating the decimal values, and 8086 calculates the general values, right? Together, they can perform a decimal value. The question of cost really depends on the implementation strategy being considered. So cost, I cannot say that there can be a drastic reduction in cost, but then based on what kind of implementation strategy, based on what kind of method that you're going to use for circuit designing to reduce the power consumption, okay, so that becomes an important factor. So based on that, I can decide how much of cost that is going to impact the circuit. For ICs, there is a fairly direct correspondence between silicon area and cost. So as much as possible, I try to reduce my silicon area, okay, so that I can pack more transistors. It's just like the real estate business, right? So even you don't get an extra inch, or probably you don't get lesser area. So the same thing happens here with the silicon area, right? Whatever is the space provided, with that you'll have to fabricate, with that you'll have to put in your modules and make sure that they go along, right? So the less space you use, it means that you're making space for the other transistors to sit, for the other modules to to be integrated, right? So it's a direct correlation between the real estate and the silicon area. So if I'm using less space, it means that I am saving a lot of cost, right? So they are directly proportional. Now, increasing the implementation area tends to result in higher packaging costs, right? So if in case I increase the area, okay, it means that I don't have space for the other modules. So if I want to have space for the other modules, for the other chips to be on the same PCB, then it means that my chip has to be smaller. So if it has to be smaller, each transistor sitting inside each IC also should be small. So not only the packaging costs, but then reduced fabrication yield, with both effects translating immediately to increased cost production, okay, product cost. So whenever we think of product, right, so it means that we are looking at the overall from the start of designing, okay, to implementation, right? So this section here becomes important for us, okay, because it talks about everything, right? It talks about packaging, it talks about fabrication, it talks about yield, and then it talks about the production cost. So all these are involved when you actually sell your IC. Okay, now VLSI designer has to explore area, time, implementation, space. What do we understand by this area, time, implementation, space? Okay, so this is an important factor, right? So whatever that we design is time bound. Okay, I just cannot have my own sweet time, okay, in saying that okay, I will just do it on my own, okay, own time, own free time. Not possible. You will have deadlines to look into, right? So each project will start off with a specification, and then you'll have to keep designing things. Then as the deadline approaches, right, you'll have to keep working till the product is finished, right? So here you can think of this area time concept. Okay, so less area and less time, all these should be kept in mind. So attempting to strike a reasonable balance between these often conflicting objectives. So there's something called optimization. So you optimize to a point where you cannot go further. You just cannot go further, but then you'll have to stop doing it. Okay, so that is called the optimized point. But area and time are not the only metrics by which we can measure implementation quality. Power consumption is yet another criteria. So not only area and time, it's not only finishing the circuit faster, designing faster, okay, not only making sure that the circuit is small, but then power becomes a very important factor. Okay, now why is it so important? Why is the power so important? Just because we know that now power is involved with everything, isn't it? Power is involved with everything. So without that, it becomes very difficult for us to manage things. Just imagine if you have to keep charging your phone for every 5-10 minutes. I don't think so none of you would purchase that, isn't it? Just because it has good features, okay, doesn't mean that the battery also could be bad, right? Okay, so moving on, power considerations were often of secondary concern. Now, what do we understand by the secondary concern? It means that it was not given so much of importance. Okay, it was only before that they were only planning to make the make the circuit better. Okay, but then thinking of having a better optimized low power consuming circuit was never thought of, right? Okay. So power was actually, thought of like a second thought, or probably they never thought of power consumption. Okay, but recently low power has been taken into consideration. Okay, so there are exceptions to this rule. For example, designers of portable devices such as wristwatches have always placed considerable emphasis on minimizing power in order to maximize battery, right? So this is what we have been looking into. So they knew that, yes, we need to have low power circuit which can actually make the wristwatches work for a long time. Just imagine, once we replace the battery, I'm sure that, for more than a year, you wouldn't be bothered of it, right? So most of the batteries, they last for more than a year and a half, right? So low power was very much taken into consideration in these wristwatches. But then as I was mentioning in the start, most of the devices have become digital, and we are trying to get things modernized, right? So everywhere you see there's a screen. Okay, your system has a screen, your smartphone has a screen, right? That's the way you engage with your device. So having a bigger screen again will lead to more power dissipation, more power consumption, right? For the most part, designers of mainstream electronic systems have considered power consumption only as an afterthought, which means they never thought of it, as very much important, right? It was always considered as an afterthought. So when I say afterthought, it means that it was a second thought for them. They really didn't take it very seriously. But then these days it's become a mandate for us, because everything is dealing with power. So power is being given comparable weight to area and speed considerations. So as I was telling you before, we used to only have this area and speed consideration, but then right now power also is given such importance, where we can make circuits much better, where we can have low power designs. The most visible driving factor has been the remarkable success and growth of PDAs. Okay, PDAs are personal digital assistants. Okay, cellular phones and other portable devices, only projected to increase in future. So our life has become so much accustomed, so much adjusted to these digital devices that we cannot live without it. Okay, so right now, if we are learning something, we need a digital device. Okay, so our life is very much dependent on these things. Okay, so moving on, right? So average power consumption has become critical design concern, and perhaps superseded speed and area as overriding implementation constraint. So as I was telling you before, it was only speed and power. Okay, but right now, that's not what it is. In fact, low power has become more important than speed and area. Okay, so concentration is given more on low power. If it can operate with less power for longer time, okay, so that's given a priority. The simple example of a future portable multimedia device terminal which supports high bandwidth wireless communication, bidirectional motion video, high quality audio, speech, pen based input, and full text and graphs. So we are using all of this in our smartphones, isn't it? So we are using a multimedia, right, in the form of text, in the form of image, in the form of video, in the form of live streaming, right? So multimedia is very much used. And then high bandwidth. So whenever you're getting connected probably to your home Wi-Fi or office Wi-Fi, or to the cellular networks, so there is a lot of bandwidth, or there is a lot of transfer of information from the source to destination. So you're sending a lot of packets, you're receiving a lot of packets. So you need high bandwidth. Now these days we are migrating from 4G to 5G, right? Recently the government has finished auctioning the spectrum, and we're going to experience 5G speed, right? So when we saw the migration happening from 3G to 4G, everyone were amazed, isn't it? So the same thing is going to happen for every generation that we migrate from one point to another, right? And this migration happens once in 10 years. Okay. So high quality audio, speech, pen-based input. So most of the phones these days even do have pen support, isn't it? Right. The projected power budget for such a terminal, when implemented using off-the-shelf components not designed for low power operation, goes more than 40 watts. Okay, so if you have to do all of these operations which is mentioned here, okay, and if you don't consider low power design, then it's going to take you about 40 watts, right? So that is really too high, isn't it? 40 watts is too high. You really cannot afford for such high usage of power, isn't it? So low power becomes very important in such case. So 40 watts is going to be really high power, when you don't think of low power. So that's when, this particular subject or this particular course comes into picture, right? You'll be able to know where to reduce the power consumption and how to make it much better. Even with new battery technologies such as rechargeable lithium or polymers, it is anticipated that the expected battery lifetime will increase not more than 30 to 40% over the next 5 years, right? So battery is one such thing. Now even our commuting also has been changed to battery technology, right? So it can be electric cars, it can be your electric bikes, okay? So everything has been migrated to battery powered devices. So not only that, this technology has to still mature, according to me, right? Most of the power stations, the where you can recharge your cars or probably bikes should be increased. The power outlets should be increased, so thereby the adaptability also will increase. Now these days, the cost of these batteries are huge. Okay, so once in 5 years at least you may have to replace the battery, and that is going to be the costliest component in your vehicle. Okay, so in the absence of low power design techniques, then current and future portable devices will suffer from either short battery life or unreasonably heavy battery packs unless a low power design approach is adopted. Now, very true. It's because many times, we don't think of low power design, but then if in case we concentrate on this low power design, then we are sure that our battery efficiency, our battery performance increases. Now you can imagine a heavy battery, right? Now let us say you have bought an electric bike, okay, and the battery is too heavy. Let's say it's about 20 kilos. So if it can run for about an hour, okay, and there is no any low power design adopted for that, okay, just for an hour and 20 kilos. So you cannot be reliable on your bike, isn't it? You will be in a kind of anxiety, right, as to when your battery will fail on you. So thinking of all these, right, low power plays a very important role. Now let's say you have implemented this low power design, and then the same 20 kilos is reduced to say 15 kilos. So thereby you have reduced about 5 kilos, and the bike is not carrying that extra 5 kilos, which means again your battery consumption is reduced, right? And due to this low power design techniques, instead of 1 hour, say it's giving you about 8 hours, one full day, right? So comfortably we can use it for our commuting for a day, right? So this is actually the importance of low power. If and only if these techniques are employed, right, then only things will start getting smooth. Okay. So moving on, right, here I have put up a graph, right, where you can see different technologies, right, different technologies, nickel cadmium, nickel metal hydride, right. So on one side of the axis you can see the year, and on the other side you can see how many watt hours, okay, that it's going to give. So you can see this nickel cadmium gives you approximately about 25, right, about 25. Then nickel metal hydride, you know, approximately about 35 to 40 watt hours, right? So it can be observed that battery capacity has only improved with a factor of 2 to 4 over the last 30 years, right? So as I was mentioning before, right, this battery uh, technology, right, they were not very much keen on getting the low power design done, right? So see, even after 30 years, it was probably, instead of giving 1 hour, it's giving 2 hours after 30 years, right? So which means we should understand there was not much of innovation in the field of low power VLSI design, right? So while the computational power of digital ICs has increased with more than 4 orders of magnitude, right? So I was talking to you about the number of transistors being packed, right? So that has increased, right? That has increased, and because of which, you know, it has become 4 times much better. But then battery, you know, the same level of same level of innovations were missing. So you can see here nickel cadmium battery offering about 20 watt hour per pound, so approximately about 0.5 0.6 kilos, right? So it's giving about 20 watt hours. This terminal would require 20 pounds of batteries for 10 hours of operation between recharges. Okay, so which means you know, it should be about 10-12 kilos of battery if you want to use it for 10 hours between recharges by the time the battery goes dead. Nickel metal hydride, another combination that was used, offers a little relief at 30 to 35 watt hours per pound. So which means, you know, slightly it is better. Here you're getting about 20, here you're getting about 35, which is much better, right? So that is reducing the weight by about 3.5 to 4 kilos, right? So which means as the progress happened, okay, year on year, so you can see that, you know, the graph slightly, you know, it's going higher from 70s to 80s, right? It was almost the same, right? From 65 to 70, there was slight shift that happened in 70, right? And then you can see a drastic shift happening after 89, right? 1989 to in the 90s, early 90s, you know, there was a drastic importance given to low power, right? So this is where this field started booming, low power VLSI. So you can see that, you know, it was about, say, 15. From 15, it has jumped to about 22, 23 watt hours, right? So as the capacity increases, right, you can see that the performance, the number of hours that the backup is given also does increase. Okay, so the same applies with nickel metal hydride, right? It started off in the 90s with about 28, right? And then it went on to about 38, 39 in the 95s, right? So after which also there are a lot of things, a lot of developments done, okay, but it's not shown here. So you can imagine lithium ion batteries, right? Then you know, these days lithium ion and lithium polymer is the most used. Lithium polymer is costly, right? So it's only used in high-end devices, and lithium ion is very much used these days. Even your car batteries, your bikes also do have lithium ion powered batteries. Okay, right. So moving on, we will now see what is the motivation still required in order to move into low power design. Okay. So peak power. Okay. So when I say peak power, it means that maximum dissipation. Okay. Maximum power dissipation. So that is the peak. Okay. So this peak power determines the electrical limits of design, dictates battery type and power distribution network. So not only thinking of the circuit, but then thinking of how it works, where the supply is coming, how will I use this VDD that is given to the circuit, and how am I going to drain it? How am I going to extract maximum output from it, right? Okay. So signal integrity through the R, I, and L di by dt problems. So we will be looking into quite a few equations. Okay, so this is nothing but the rate of change of current with respect to time. Okay, L into di by dt, and then through R into I. Signal integrity is something where how it starts. Okay, how much of signal that you are giving and how much of output that you are getting at the other end. Okay, so basically if you're giving about 0.75, you should be receiving 0.75. It's not that you get about 0.2 while giving 0.75. So that doesn't mean your signal has signal integrity. Okay. It is therefore essential to have peak power under control. Portability is by no means the sole driving force behind the push for low power. So it's not that devices are becoming portable and hence we need to concentrate on low power. Yes, that's also one of the reasons, but then the major reason is that integration, right? Whatever signal that I'm giving 5 volts. Yes, I expect 5 volts also at my output. Maybe lesser 0.05 here and there, plus or minus is fine. 4.95 I'm getting should be manageable, right? It shouldn't be 3 for an input of 5. So there exists a strong pressure for producers of high-end products to reduce their power consumption as well. Okay, so this is where the challenge is, right? You just cannot escape, um, the consumption of power. Okay, you should concentrate on power dissipation and make sure that your devices do not dissipate much. High performance processors dissipate as much as 30 watts. That's one of the reasons why most of the processors do have fans on them, right? So as these fans rotate, they vent out the heat that is being generated by the processor. Okay, fine. So moving on. Yeah, so this is the formula that we'll be looking into. Yeah, more importantly, it shows that the dissipation increases approximately linear with the area frequency product. Okay, so f clock is nothing but the clock frequency, how much of frequency that your clock is operating at, and the area. Okay, so this is nothing but your factor, and with a factor of 0.063 watts per centimeter square megahertz, right? So the following expression seems to hold approximately. So I cannot say that this is my only expression, but this is just an approximation of the power consumption. So you may have to remember this formula. Core power consumption must be dissipated through the packaging. Increasingly expensive packaging and cooling strategies are set up and required as chip power consumption increases. So cooling strategies, one such strategy can be, these days, even your phones have this cooling strategy. They use a gel, okay, gel which is pasted on top of the processor, and that acts as a cooling agent for your processor. And I remember few phones even released, with vapor chamber. Okay, they call it as vapor chamber. So as soon as it gets heated, immediately this there's a kind of vapor that gets formed, and then that starts cooling your processor. Then they said, okay, that is not fine, let us use a gel type. Okay, so gel was used around the processor, so that by the time this gets heated, it takes a lot of time, and then so that in that way they were able to reduce the power consumption. Consequently, there is a clear financial advantage to reducing the power consumed by high performance systems. So not only these strategies, but then we'll have to employ few more things which can actually work on low power. So I hope you have now understood as to why do we need low power and how important it is in reducing the power consumption for each and every circuit that we design.